In this A3 tutorial, we're going to look at harmonics and what they are, and we're going to look at them in the time and in the frequency domain. So the first question that we really need to ask here is, or to understand, is what is a harmonic? And the best way of understanding this is to look at waveforms in the time domain. And we can have a nice, beautiful, simple sine wave, and there it is there. So that's a simple sine wave. It's pure, it's obviously sinusoidal, and it has no harmonics. On the other hand, a complex wave is pretty much every single other type of waveform. Now, before I sketch one of these, it needs to be a waveform. It needs to be repetitive. Okay? So, for example, a complex wave that is non-sinusoidal and is repetitive, sinusoidal, excuse my spelling, it could be some form of square wave, it could be a triangular wave of some type, something like this. It could be a sawtooth, which goes, can go like this. It could be, anything. One common one that we encounter in power engineering and power electronics is as a result of SCRs. Now, a waveform as a result of an SCR takes our nice, beautiful sine wave, and an SCR is basically a diode that can do a controlled rectification. So a normal diode would pass everything in the forward direction and block everything in the negative direction. And we'd end up with a waveform like this, and so on. And this repeats itself. We've got one here, and we've got one here, and forever. And that's a basic diode waveform. But in SCR, we can delay the turn on. So it might be like this. We might delay the turn on in time to here. So our resultant waveform looks like this. Now, this is a complex wave, okay? It's repetitive, it's not a sinusoid. It will, by definition, have harmonics. And harmonics are frequencies that are the multiple of our fundamental sine wave. And frequency. So, if this is our fundamental wave here, our second harmonic, we'll call this here F1 for fundamental. Our second harmonic of this particular frequency here would go through twice as many cycles because it's twice the frequency. So we would need to go through 2 complete cycles. So a waveform that looked like that would be our second harmonic. Now note I've ignoring the amplitude here. That's a totally separate thing. We'll come to that later on. We're just talking about in the frequency domain. So our second harmonic would go through like this. Our third harmonic would have 3 complete cycles within the 1 cycle of our fundamental. Now, that's kind of explained what a fundamental is and what a complex wave is. What we'll do now is we'll work back. We'll take a fundamental and a harmonic, and we will build up a complex wave. So let's take, for example, a 50 Hertz waveform, and we will say it's got a peak voltage of 325 volts, which is the same as saying a RMS of 230. And we will put in, so this is our fundamental, which we call F1, and we'll put in a second harmonic, which we'll call F2, and by definition the frequency is 2 times that, so that will be 100 Hertz, and we'll give it a value of, well, we'll give it an RMS of 100 volts, so it's going to be a very big one, which 100, that makes that VP equals 135 volts. So we can take these two, our fundamental and a harmonic, we can put them together and we can see what sort of resulting complex wave we will get. And it's quite simple to do that. We can simply draw it in the time domain here. And here's our fundamental, F1, and I've said that has a peak voltage of 325. And we're going to put a second harmonic in there that has a peak voltage of 135. So 325, 130 would be, oh, it's about 170, so we're around about here, whatever. So it's got to go through these points round about here. Oh. And this is our second harmonic. Our resulting waveform, the complex wave that we would get from these two particular harmonics in the time domain, is simply the sum of them. And we can go through and we can find the sum of these very simply by adding them up in their values. So we can start here. They've both got a value of 0. 0 plus 0 equals 0. Similarly, the peak of our fundamental plus the 0 of our second harmonic crossing, our 0 plus that peak value there will equal that peak value there. 0 plus 0, 0 plus 0, 0 plus the negative peak. So our complex wave is going to go through those points there, but we probably need a few more data points. So we'll come back and we'll look at this one here, at this particular point here, which would be about 1/8 of a cycle. We can see that it would be that point plus that point there, so our resultant would be up here somewhere. At this particular point in time here, we've got this value plus the negative this value, and that would probably be, I would say it's about a finger width less than that, so it's right about here somewhere. Similarly, at this particular point in time, probably about there, and that point in time, there plus there equals here. So our resulting waveform is going to go through these points which we've identified. So if we were to draw a line through that, we would get something that looks a little bit like that. This here, waveform here, is our resultant waveform. It is what we call a complex waveform because it's not a simple sinusoid. And as I said, it's complex, and that is the waveform that we would see. If we were to put an oscilloscope in a circuit that had this fundamental and this harmonic, this waveform here is what we would see on our oscilloscope. In the frequency domain, if you were to plot the harmonics, we get a plot that looks like this. We have frequency on the x-axis and the magnitude on the y-axis. And here we've only got two waveforms, so we would see our first one here at 50 Hertz, and it would show like this. And normally when you, on most oscilloscopes like the Tektronix ones that we have here that do harmonic plots, most of them show the RMS voltage here. If you're in an exam and you get asked a question like this, it doesn't really matter which you put on this axis, on the y-axis here, provided you're consistent. So we could call it 325 for peak, or we could call it 230 RMS. And we have got our second harmonic, 100 Hertz. And this was at 100 volts RMS, which equals 130 volts peak. So of a complex wave with a fundamental and one harmonic, I drew the second harmonic. If we add those together, our resultant wave looks like that in the time domain, and this is what it would look like in the frequency domain. In terms of a mathematical representation of this, there are two ways that it's often represented. One of them is called the simple way, and the other one is called the complex way. And both convey pretty much the same information, but they take different ways of going about doing it. So the simple way is simply, it would say something like the fundamental plus a percentage of the fundamental at whatever harmonic. So we would say over whatever of the second harmonic plus whatever of the third harmonic plus whatever of the fourth harmonic, and so on. This particular one we've got here, we would represent in the simple way of saying our fundamental plus our second harmonic, and our second harmonic is 135 divided by 325 is close enough. It's 41%. So we'll call that 40%, which is 2/5. So we would say that it's our fundamental plus 2/5, or 40% of the second harmonic. This number here is relative to the magnitude of that. Okay, everything here is relative to the fundamental. In this particular one here, we don't have a third harmonic or a fourth harmonic or anything, so these terms here would all go to 0 in this particular example we've got here. So that's it there in the simple. That would represent that waveform there. The complex form says pretty much the same thing, but it takes a different way. And that way is represented as being the peak, and then it says that it's a sine wave, and then it goes something like this. So what we're basically doing is they're saying it is this sine wave plus this sine wave plus another sine wave plus the voltage, the peak voltage, and it's a sine wave, 2 pi f as a function of t and whatever theta, etc. So this is the peak voltage. This is telling it's a sine wave. 2 pi is over 2 pi over 2 cycles. The frequency is a function of time plus any phase shift. So the phase shift is whether any of these waveforms here have been shifted this way or that way. In my example that I've done here, neither of them have got any phase shift, so these terms will be 0. So we can represent my complex wave that I've got here, down here like this. It's 325, which is a sine wave, of 2 pi, our fundamental frequency is 50 as a function of time. There is no phase shift, so that term goes to 0. The next one we have has got a peak voltage of 135. It's also a sine wave. 2 pi, the frequency is 100 Hertz. And again, this term goes to 0 because we've got no phase shift in our second harmonic. And there's no other ones, so that's simply it. So here we have two representations, the simple representation for this complex wave, here it is here, and our complex representation for the very same wave here. Peak voltage, saying it's a sine wave, 2 pi is the frequency, it's a function of time, and in this particular one there's no phase shift. In an exam, for example, you could be given a complex wave as an expression like this, or you could be given a complex wave as an expression like this. And your job would be to go through and identify all these particular terms out of this expression and understand what's going on here. What I've done here in this tutorial, just to recap, is I've shown that a complex wave is a series of sine waves which can be all added together to create this resulting complex wave. I used a very simple example with only a fundamental and a second harmonic. As an aside, if this had been a third harmonic, our resultant waveform, if you go off and do this yourself, would look something like this. Okay? Because our third harmonic would have 3 cycles through here. 1, 2, 3. And if we were to add up our fundamental, if we would add up here our fundamental with our third harmonic here, we would end up with something that looked like this. So we can build up any complex wave made out of sine waves. As you go on with your engineering career, you'll go into a lot more mathematical ways of exploring the same thing. You can take one of these waveforms and do what's called a fast Fourier transform, and you will obtain all the harmonics and the frequencies and the all that sort of stuff that make it up. What I've done here is just a very simple introduction to harmonics in the time domain and in the frequency domain. Thank you for watching.